Welcome to my channel PMT, that is Paid Passion Behind the Movie and Dance Show. Today's topic is hydrodynamics. The study of fluid in motion is known as hydrodynamics. A steady state and turbulent flow. The flow of the fluid is said to be a steady state if at any given point the velocity of each passing fluid particle remains constant in time, otherwise turbulent. As shown in the figure, if the velocity at p remains v1 at every time, then the flow will be, at this point the flow will be called a steady state. Similarly, at q, if its velocity is always v2 and at r its velocity is always v3, then the flow at this point will be called a steady state flow. Each particle flows a smooth path and the path of the particles do not cross each other. Critical speed. The speed beyond which a steady flow of liquid becomes turbulent is called critical speed. The speed beyond which the steady flow of liquid becomes turbulent is called critical speed. For example, consider the point P. Now, we increase the velocity and velocity is increases and a time reaches when at point P the velocity every time velocity is changing, and so at that time the flow at this point P will be called turbulent. A streamline. The path taken by a fluid particle under a steady flow is a streamline. It is a curve whose tangent at any point is in the direction of the fluid velocity at that point. The path taken by a fluid particle under a steady flow is a streamline. It is a curve whose tangent at any point is in the direction of the fluid velocity at that point. Consider a fluid is flowing as shown in the figure and its graph is shown. Then at this point, if we take tangent, then it will represent the velocity at this point. Similarly, at this point and another point, the velocity will be represented at v2 after taking tangent to that point. And this line is called a streamline. Tube of flow. A bundle of a streamline is called tube of flow. The figure is shown as shown in the figure, tube of flow. Why two or more streamlines cannot cross each other? Answer: no two or more streamlines can cross each other, for if they do, an oncoming fluid particle can go either one way or the other and the flow will not be steady. Ideal liquid. A liquid which is incompressible, non-viscous and isotropic is called an ideal liquid. Equation of continuity. When an ideal liquid flows in a steady state through a tube of non-uniform cross-section, then the product of the area of cross-section and the velocity of flow is same at every point in the tube. Here a tube is shown. Consider the point P. At this the velocity of fluid is Vp and the area of cross section is AP. Similarly, at R, point R, the velocity is VR and area of cross section is AR. And similarly, at Q, the velocity is VQ and area of cross section is AQ. Then, according to this law, velocity in area at all these points will be equal. That is, AP into VP will be equal to AR into VR will be equal to AQ into VQ. Consider a tube of flow of liquid as shown in the figure. Since the liquid is incompressible, the mass flown at point P in time delta T is equal to the mass flown at R in the same time interval. Hence, delta M P equals to delta M R. Now, this mass will be given as Vp into delta T into AP into rho. Vp into delta T into AP into rho equals to VR into delta T into AR into rho. This implies Vp into AP equals to VR into AR, proved. Or we can write this as Va equals to constant, that is velocity into area in a tube is constant. Equation 1, where Vp equal to velocity of liquid at P, VR equal to velocity of liquid at R, AP equals to area of cross section of tube at P, AR equal to area of cross section of tube at R, rho equal to density of liquid. Equation 1 is called equation of continuity, and it is a statement of conservation of mass in flow of incompressible fluid. Bernoulli's equation. Our next topic is Bernoulli's equation. First, we see the statement of Bernoulli's equation. It relates the pressure, flow speed, and height for flow of an ideal fluid. As we move along a streamline, the sum of the pressure P, the kinetic energy per unit volume 1 by 2 rho V square, and the potential energy per unit volume rho GH remains constant, that is P plus 1 by 2 rho V square plus rho GH equals to constant. Let's prove this equation. For proving, consider a fluid moving in a pipe of varying cross-sectional area and varying height. The flow of fluid is a steady state. The velocity of fluid at different points is different due to consequence of equation of continuity. Thus, a force is required to change the velocity. The pressure must be different at different positions. The situation is shown in the figure. Consider the flow at two regions, 1 and 2. The velocity, pressure, and force at these 2 points are shown in figure. In a small time interval delta t, fluid at 1 moves from B to C, and at 2 from D to E. The work done on the fluid at left end is W1 equals to P1A1 into V1 delta T, or equals to P1A1 into delta L1, or equals to P1 into delta V1, where V1 is the volume of the element. And the work done on the fluid at right end is W2 equals to minus P1A1 V1 into delta T, P2A2 into delta L2 equals to minus P2 into delta V2. Here delta V2 is the volume at point 2. So total work done on the fluid is W equals to W1 plus W2 equals to P1 into delta V1 minus P2 into delta V2. Equation 1. From equation of continuity, A1 V1 equals to A2 V2. This implies A1 V1 into delta T equals to A2 V2 into delta T. Or this implies A1 into डेल्टा एल A1 equals to delta L1 equals to A2 delta L2. This implies delta V1 equals to delta V2 equals to delta V. So equation 3 becomes W equals to P1 into delta V minus P2 into delta V equals to under bracket P1 minus P2 into delta V. Equation 4. Potential energy at T1 U1 equals to delta M1 into G into H1 equals to rho into delta V1 into G into H1 equals to rho into delta V into G into H1 because we have assumed delta V1 as delta V. Similarly, at potential energy at 2 U2 equal to delta M2 into G into H2 rho into delta V2 into G into H2 rho into delta V G H2. Hence, change in potential energy delta U equals to U2 minus U1 rho into G into delta V into under bracket H2 minus H1. Equation 5. Now, calculation of kinetic energy. Kinetic energy at 1 K1 equals to 1 by 2 delta M1 V1 square equals to 1 by 2 rho delta V1 into V1 square equals to 1 by 2 rho V1 square into delta V. Kinetic energy at 2 K2 equals to 1 by 2 delta M2 into V2 square 1 by 2 rho delta V2 into V2 square 1 by 2 rho V2 square into delta V. Hence delta K equals to K2 minus K1 equals to 1 by 2 rho into delta V into under bracket V2 square minus V1 square. Equation 4. Here the work done by the force is other than the conservative force of gravity. So the work done is equal to the change in mechanical energy of the system. Hence we can write work done equals to change in kinetic energy plus change in potential energy because mechanical energy is equal to the kinetic energy plus potential energy. Hence W equals to delta K plus delta U. This implies P1 minus P2 into delta V equals to 1 by 2 rho into delta V into V2 square minus V1 square plus rho into G into delta V into H2 minus H1. This implies P1 minus P2 equals to 1 by 2 rho into under bracket V2 square minus V1 square plus rho into G into under bracket H2 minus H1. That is, work done per unit volume equals to change in kinetic energy per unit volume plus change in potential energy per unit volume. Now, we can write P1 plus 1 by 2 rho V1 square plus rho G H1 equals to P2 plus 1 by 2 rho V2 square plus rho G H2. Hence, P plus 1 by 2 rho V square plus rho G equals to constant. Hence, this is the Bernoulli equation. If fluid is at rest, that is velocity is 0 everywhere, Bernoulli's equation becomes P1 plus rho G H1 equals to P2 plus rho G H2 or P1 minus P2 equal to rho G H2 minus rho G H1 equals to rho G into H2 minus H1. This implies delta P rho G into delta H or rho G into H, where H is the change in height. Same as derived in the case of hydrostatic equation. Now, next topic is our speed of efflux and Torricelli's law. The speed of efflux from an orifice of an open tank is equal to that of a freely falling body, that is V equals to under root 2gh. Here a tank is shown and a orifice is made. Here the velocity of flow of liquid at this orifice will be equal to V equals to under root 2gh. where h is the height of free surface from orifice. This is the Torricelli's law. Derivation. Consider a tank containing a liquid of density ρ with a small hole in its side at a height y1 from the bottom. From equation of continuity, V1A1 equals to A2 V2A2. Where V1 is the velocity of liquid at orifice and V2 is the velocity of liquid at point 2, that is velocity of layer of surface, free surface, and A1 is the area of orifice and A2 is the area of free surface. Now V2 equals to A1 by A2 into V1. This is equation 1. Now if A2 is very greater than A1, then A1 by A2 equivalent to 0. Hence from 1, V2 equivalent to 0. This means fluid is approximately at rest at the top. It is assumed again applying Bernoulli's equation at points 1 and 2, we have P1 plus 1 by 2 rho V1 square plus rho g y1 equals to P2 plus 1 by 2 rho V2 square plus rho g y2. Now since P1 equals to P atmospheric pressure, P1 is equal to the atmospheric pressure and P2 equals to P and V2 equals to 0, the equation becomes Pa plus 1 by 2 rho V1 square plus rho g y1 equals to P plus rho g y2. This implies 1 by 2 rho V1 square equals to P minus Pa plus rho g y2 minus rho g y1 equals to P minus Pa plus rho g into y2 minus y1 equals to P minus Pa plus rho gh. This implies V1 square equals to 2 into under bracket P minus Pa by rho plus 2 rho gh by rho. Hence V1 equals to under root 2 into under bracket P minus Pa by rho plus 2 gh. Equation 2. Case 1. If the tank is open to atmosphere, then P equals to Pa. So equation 2 becomes V1 equals to under root 2 gh. This is the Torricelli's law. Case 2. If P is greater than Pa, that is pressure is greater than atmospheric pressure, and 2gh may be ignored, the speed of efflux is V equals to under root 2 P minus Pa by rho. This is the case of rocket propulsion. Our next topic is Venturi meter. It is a device to measure the flow speed of incompressible fluid. It consists of a tube with a broad diameter and a small constriction at the middle as shown in the figure. A manometer in the form of U-tube is also attached to it with one arm at the broad neck point of the tube and the other at constriction as shown in the figure. Here the situation is shown. The barometer of one end is at broad end and the broad neck, and other end is at narrow neck, and A is the area of cross section at constriction, and capital A is the area of cross section of broad neck. Here fluid velocity is V1 and density of liquid is rho, and at constriction fluid velocity is V2, and in the barometer S2 point P2 is at H2 distance from the constriction. Let rho m is the density of liquid in the barometer. That now from equation of continuity V1A equals to V2A, this implies V2 equals to V1 into A by A, equation 1. Applying Bernoulli's equation, we get P1 plus 1 by 2 rho V1 square plus rho G H dash equals to P2 plus 1 by 2 rho V2 square plus rho G H dash. This will be P1 minus P2 1 by 2 rho V2 square minus 1 by 2 rho V1 square equals to 1 by 2 rho V1 square A square by A square minus 1 by 2 rho V1 square, or P1 minus P2 equals to 1 by 2 rho V1 square under bracket A by A का whole square minus 1. Now in manometer PA equals to PB. This implies P1 equals to P2 plus rho m into GH. This implies P1 minus P2 equal to rho m into GH, equation 3. Hence from equation 2 and 3 we have two and 3 1 by 2 rho into V1 square into under bracket A by A to the whole square minus 1 equals to rho m into G into H. This implies V1 square equals to 2 into rho m into G into H by rho into under bracket A by A का whole square minus 1. Hence V1 equals to under root 2 rho m into G into H divided by rho into under bracket A by A to the whole square minus 1 equals to under root 2 rho m G H by rho into A by A square minus 1 to the power minus 1 by 2. Thus we have V1 equals to under root 2 rho m into G into H by rho into A by A to the whole square minus 1 to the power minus 1 by 2. Answer given. Example: the flow of blood in a large artery of an anesthetized dog is diverted through a venturi meter. The wider part of the meter has a cross-sectional area equal to that of the artery, A equals to 8 mm square. The narrower part has an area A equal to 4 mm square. The pressure drop in the artery is 24 Pascal. What is the speed of blood in the artery? The density of fluid is 1.0. The density of fluid is 1.06 into 10 to the power 3 kg per meter cube. This answer: the ratio of area A by A equals to 8 meter square by 4 meter square equals to 2. Hence we have formula V1 equals to under root 2 into rho m into G into H by rho into divided by rho into under bracket A by A to the whole square minus 1 to the power 1 by 2. Using all value we get 0.125 meter per second. Answer: blood flow and heart attack. Bernoulli principle helps in explaining blood flow in artery. The artery may get constricted due to accumulation of plaque on its inner walls. In order to drive the blood through this constriction, a greater demand is placed on the activity of the heart. The speed of flow of the blood in this region is raised, which lowers the pressure inside, and artery may collapse due to external pressure. The heart exerts further pressure to open this artery and forces the blood through. As the blood rushes through the opening, the internal pressure once again drops due to same reasons, leading to a repeat collapse. This may result in heart attack. Now, dynamic lift. It is the force that acts on a body such as aeroplane being a hydrofoil or a spinning ball by virtue of its motion through a fluid. Magnus effect. Ball moving with a spin. When a spinning a spinning ball is thrown, it deviates from its actual path due to pressure difference in upper and lower part of the ball. This is called Magnus effect. The situation is shown in the figure. Aerofoiler lift or aircraft wing. The wing of a aircraft or aerofoil is shown in the figure. It is solid piece shape to provide an upward dynamic lift when it moves horizontally through air. When the aerofoil moves against the wind, the orientation of wing relative to flow direction causes the streamlines to crowd together above the wing more than those below it. The flow speed on top is higher than that below it. There is an upward force resulting in a dynamic lift of the wings, and this balances the weight of the plane.